This is part 2 of Objective 3.1, Intermolecular Forces. Our topic is to explain the relationship between the chemical structures of molecules and the relative strength of their intermolecular forces when the molecules are of the same chemical species or of two different chemical species. And our skill is model analysis. The second key point of this objective is that the dipole moment of a polar molecule leads to additional interactions with other chemical species. So here we have a polar molecule, HCl, and because it's by nature of it being polar, that means that there's a molecular dipole. So there's a disparity of electrons. So chlorine, which is on this side, is more electronegative than hydrogen, so it has a slightly negative charge, whereas hydrogen has a slightly positive charge because the electrons in this bond are closer to chlorine. So this molecule does not have a temporary dipole, it has a permanent dipole. The chlorine is always slightly negative, the hydrogen is always slightly positive. That exists always and in every hydrochloric molecule. So this can cause a dipole-induced dipole interaction. These are present between polar and non-polar molecules. These forces are always attractive. The strength of these forces increases with the magnitude of the dipole of the polar molecule and with the polarizability of the non-polar molecule. So here we have a non-polar molecule, chlorine, Cl2. And so a non-polar molecule can have a temporary dipole that's created by a polar molecule. So when we put this slightly positively charged hydrogen next to this molecule, we induce a dipole. We cause the electrons in this molecule to be attracted to that slightly positive charge, and therefore the right side of this molecule is now slightly negatively charged. And so this attraction in between the Cl2 molecule and the HCl molecule is a dipole-induced dipole interaction. It's a dipole has been created. A dipole is induced from a dipole, from a molecule that is polar, that has this dipole. And if Cl2, if the non-polar molecule is has more polarizability, that means there are more electrons could be attracted to hydrogen, or if this molecule was flipped, more electrons would be repelled from the chlorine. That would increase this attraction. And if the charge disparity of our polar molecule is larger, so if, let's say this was HF, because fluorine is more electronegative than chlorine, there's going to be a larger dipole because there's a larger difference in electronegativity. So this would be a slightly larger positive charge, a slightly larger negative charge, and that would also cause a stronger interaction. And here you see the same thing, I and Cl inducing this dipole, causing the electrons to be repelled in the xenon because chlorine has a negative charge. Then we also have dipole-dipole interaction. So dipole-dipole is an interaction between polar molecules. So two molecules that have that are polar, that have a dipole. That's why it's called dipole-dipole. And dipole means two poles or two charges. So a positive and negative side, a positive and negative charge means that it has a dipole. The interaction strength depends on the magnitudes of the dipoles and their relative orientation. Interactions between polar molecules are typically greater than those between nonpolar molecules of comparable size because these interactions act in addition to London dispersion forces. So in the last video, we talked about how every single molecule has London dispersion forces because electrons are constantly moving around and can be more concentrated on one side of the atom or the molecule than on the other. And so HCl and H2O have London dispersion forces as an intermolecular force, but they also have a dipole-dipole interaction with a permanent dipole as well. And so this is a stronger, so polar molecules tend to be more strongly attracted to one another. And then we have ion dipole interaction. So an ion dipole force is an attraction between an ion and a polar molecule, or an ion and a dipole. These tend to be stronger than dipole-dipole forces. And that's because an ion is much larger charge than a polar molecule. This is a completely positive charge. Maybe it's +1, maybe it's +2, whatever it is. Whereas this lowercase delta, this means that it's a partial charge. It's not quite a +1 charge because the electrons are still shared in between the hydrogen and the chlorine. They're just a little bit closer to the chlorine. And so because we have a larger charge, we have a stronger attraction. So this is a stronger force. And so you can see with water molecules, when salt, sodium chloride, dissolves in water, what happens is that the ions, the sodium ions and the chlorine ions, actually separate because the positive charged hydrogens can surround the chlorine ion and the negatively charged oxygens can surround the sodium ion. And so we have this ion dipole interaction. So based on Coulomb's law and the information in the table above, or below in this case, which of the following cations is most likely to have the weakest interaction with an adjacent water molecule in an aqueous solution? Okay, so whenever you hear Coulomb's law, you should be thinking of two things. We're thinking of charge, which is represented by a Q, and we're thinking radius. So charge generally trumps radius and is more important in this formula. And so we're talking about an attraction with a water molecule. So water molecules have a slight charge, but since all of these will be attracted to the water molecule, we don't need to really take into account the charge of the water molecule. We're just comparing the charge of the ions. And so notice In has the highest charge. Okay, that's going to mean the strongest attraction, but we're looking for the weakest attraction. So that would be between lithium and sodium. They have the lowest charges. So this is going to have the weakest attraction. So now we have to think about radius, and sodium has a larger radius, and therefore it also, that would be a weaker attraction than lithium. So sodium is our correct answer. Our third key point is that hydrogen bonding is a strong type of intermolecular attraction that intermolecular interaction that exists when hydrogen atoms covalently bonded to the highly electronegative atoms, nitrogen, oxygen, and fluorine, are attracted to the negative end of a dipole formed by the electronegative atom, nitrogen, oxygen, and fluorine, in a different molecule or in a different part of the same molecule. So again, these are intermolecular attractions between two molecules. And I like to remember this because you can't have enough of hydrogen bonding. So NOF, NOF, nitrogen, oxygen, fluorine, the three most electronegative atoms, that's where hydrogen bonding exists. So you can have hydrogen bonding exists between two adjacent molecules. So here we have a hydrogen that's bonded to an oxygen and an oxygen that's bonded to a hydrogen. So then this intermolecular attraction between the oxygen and the hydrogen of two adjacent molecules is a hydrogen bond. Here we have a hydrogen bonded to a fluorine and a hydrogen bonded to a fluorine. So the intermolecular attraction between the hydrogen and fluorine is a hydrogen bond. And you can have it between two different molecules. So here we have NH3 and H2O, and this is a hydrogen attracted to an oxygen. And this bond is actually incorrect. It should be going to our nitrogen because the nitrogen has slightly negative charge, the hydrogen has a slightly positive charge, and the oxygen is slightly negative. So the oxygen could be attracting to one of the hydrogens. But this is a hydrogen bond. The attraction between a hydrogen from one atom and that hydrogen has to be bonded to nitrogen, oxygen, or fluorine, and it's attracted to a nitrogen, oxygen, or fluorine that's bonded to a hydrogen in another atom. So that's hydrogen bonding, and that is the strongest type of, it's a type of dipole-dipole interaction because both of these are polar molecules, and it's the strongest type of dipole-dipole interaction. Okay, so check for understanding 4. Identify the intermolecular forces present in each situation. So in a cup of pure water, a cup of tap water, air, a mixture of water and oil. So in a cup of pure water, we have London dispersion forces because London dispersion forces exist in all molecules, every single molecule, because the electrons in the atoms can shift from side to side of each atom and can sometimes even shift around the molecule. Since these are polar molecules, we have dipole-dipole forces. And then we have this hydrogen bonding because we have hydrogen bonded to an oxygen, hydrogen bonded to an oxygen. So this is also hydrogen bonding. Here we have a cup of tap water. So that's water with some ions in it. So in between the water molecules, we would have the same as we had in this slide. We would have London dispersion forces, dipole-dipole, and hydrogen bonding. And then we also have this interaction with the ion. So we also have ion dipole forces. With air, we have, and this is just a specific sample of air made up of oxygen, nitrogen, and carbon dioxide. There's a lot more molecules in air, but all of these molecules are non-polar, and so therefore our only force is London dispersion forces. There's no permanent dipole. None of these have a permanent negative or positive charge in the molecule. It's all temporary, and so it's just London dispersion forces. And then we have a mixture of water and oil. So oil is nonpolar. So in between the oil molecules, we just have London dispersion forces. In between the water molecules, we have London dispersion forces, dipole-dipole forces, and hydrogen bonding. And then at this layer, in between the water and the oil, we have dipole-induced dipole, because the dipole from the water, right, if this is a positive charge, these hydrogens are positively charged, it's going to attract the electrons that are in our oil molecule and therefore induce a dipole. So this side of the oil molecule would be slightly negative, at least temporarily. We have all of those.